simple recurrence relations. Now we need to start solving recurrence relations. So we will solve recurrence relations of several different types. Actually, in your Math 3000, you have some experience solving recurrence relations. Some of the methods we use there, we need to use here. All right, so let's start. First, we just solved the recurrence relations from the Tower of Hanoi problem. We derived, then we need to solve it, find a solution. All right, so Tower of Hanoi problem, we do efficiency analysis. The basic operation, disk move. We treat each single disk move as the basic operation. So now we count the number of disk move operations. All right. Okay, First, we define that function. For a problem of size n, the number of disk moves to solve the whole problem, C of n. All right. Then we derive the recurrence relation on this function. It's pretty simple, pretty straightforward. Because if we recall the procedure we did in the previous video, you can see to solve the whole problem, we split into 3 parts. 2 of the 3 parts, we solved the problem P of n minus 1. So that corresponds to C of n minus 1. But we did it twice. So the number of disk moves 2 times C of n minus 1. In the middle, there is 1 disk move on the bottom largest disk. So we get a recurrence relation as simple as this one. Although it's pretty simple, but so here the initial condition here it should be C of 1, right? C of 1. So the typo here. We need to fix it. C of 1 equals 1. That's the starting base condition. All right. Now we need to solve this recurrence equation. How to solve it? Here we need to use some math special method here. Use some math operations. Transform the formula. How to use? It may not be that straightforward. You need to do something special here. So let's do something special to solve the recurrence relation. How to transform the formula? Because if you try to solve directly from this equation, it may not be that easy. You can try by yourself. It may not be that easy. When you have this situation, a general way to do it, transform the current formula to a different form. Then you may have a good view of it, and then you have a good chance to solve it. Here, let's do it. All right. When we transform the formula, the question is, how do you transform the formula, right? Now, it's not easy because usually people do not know how to transform the formula. Here, I give you some guideline here. Explore the similarity in structure. explore the similarity in structure. What do you mean explore the similarity in structure? Here, let me show you in this example. This is our original formula. If you look at the two sides of the equation, left-hand side, right-hand side, the structure is different. What do you mean the structure is different? Because at the left-hand side, you have a single term, right? Right-hand side, you have two terms, you have a plus sign. So the structure is different. Now the question is, can you do some, equivalent form change such that the structures of both sides are similar in some way? So that's the point. So let's do it here. Because here, right-hand side you have plus 1, left-hand you do not have plus 1, right? You do not have anything plus. All right. To make as close as possible, we do this. We add 1 both sides of the equation and see what happens. We add 1 both sides of the equation. So the right-hand side at plus 2. When we do this, it's an equivalent change, right? Equivalent form change, but the result is quite different. Why? Because 2 here, 2 here. You can take common factor 2 out. After you factorize 2 factor, inside the parenthesis, c of n minus 1 plus 1, and look at this, c of n plus 1. Do you think they have the similar structure, mathematical structure? C function plus 1, right? A C function of different sizes. The size here is n, here the size is n minus 1. Only the sizes are different. Then plus 1, the structure the same. That's what we need. Because if you have that kind of similar structure, now we can simplify it by introducing a new function d of n. We represent that c of n plus 1 as a new function d of n. Then this circle, it becomes d of n minus 1. The same function, but we just change the size number, n minus 1. After that, you can see we derived a new recurrence relation, and this one is simpler. D of n equals 2 times d of n minus 1, and there is no plus 1 part. You can see after this formula transformation, we eliminate that constant term, plus 1. So for this new recurrence relation, do you think it is easier to solve than the old one? Yes, it is easier to solve. So let's try to solve this new equation. Okay, but we need a base condition. D of 1 equals 2. Because D of 1, based on the definition, you plug in 1 here, 1 plus 1, you get 2. Okay, you get 2. So D of 1, you get 2. Initial condition. Now we are ready to solve the new recurrence relation. All right, plug in. All right, so we keep doing this because d of n minus 1 equals 2 times d of n minus 2, and so on. But we can replace d of n minus 1 by 2 times d of n minus 2. So we get 2 squared times d of n minus 2. And keep doing like this. But here there is a problem. How do we keep track of the formula change in this way to the end? Usually we may feel hard to keep track of it, right? We feel hard to keep track of it. Here, So let me tell you the method we used before. Here we used another time. Invariant method. Remember? Invariant. Quantity. Try to find some invariant quantity. Then you will keep track of the formula change all the way to the last one. Yeah, let's do it. All right. So here, look at the exponent of 2. So here, 2. Exponent of 2, that's 1. N minus 1, the size. Look at that. Add these two numbers. 1 plus n minus 1. What's that number? Equals n. Okay? All right. Then here, exponent 2, the problem size n minus 2. 2 plus 2, that's also n. Can we get this invariant? The sum of the exponent number and the problem size is the fixed number n. Always like that. Okay. Yeah. So then we keep doing, so invariant idea. Then to the last one, exponent number n minus 1, then the size number is 1. N minus 1 plus 1, that's n. So in this way, we know it's correct. We use this invariant idea. We can keep track of the formula change all the way through the last one. Yeah. All right. D of 1 equals 2. 2 to the n minus 1 times 2. That's 2 to the nth power. D of n equals 2 to the nth power. Go back to C of n, because C of n equals D of n minus 1. So we get a final solution. C of n equals 2 to the n minus 1. That's the answer. Now, if you want to check if it's correct, you can go back to the original. You plug in 1 there, it's true. Then you verify the equation. You can easily see this is also true. Yeah. That's how we solve this problem. Simple recurrence relation, but we use some mathematical thinking, analysis method to solve, especially this invariant method. Very useful. Okay. All right. So we finish our video number 3 here.